we are going from a velocity graph to an acceleration graph. So what are we going to do? Slow. All right, we're going to do slow, but we're going to do it quickly. Okay? So, all right. All right. Luckily, the speaker on this thing isn't the best, so some of those little side conversations. Huh? Never mind. Moving on. Okay, so we're going to zoom in. We're going to take the slope of a velocity graph, will give us acceleration. Acceleration, therefore, is the change in velocity divided by the change in time. All right, so we are going to go ahead and we are going to calculate the acceleration for each one of these bits, okay, each one of these portions. So, acceleration of A, therefore.
Is this in the homework?
Yeah, this is the acceleration graph that was last night's homework.
Are you okay if I copy that?
No.
Well, I mean, I did it, like, I changed it.
Yeah. Okay, so this is our acceleration. We have a change in velocity. We go from 0. Hang on. We're going to go from 0 to 5 seconds. It's 5 meters per second. And we're going to do that over a span of 5 seconds. So this is what it looks like. 5 meters per second divided by 5 seconds. 1 meter per second per second. Meter per second squared. Okay? So for segment B, acceleration of B, we're going to do the same thing. It goes for a change in velocity of 10. And it has a time period of 5. So we've got 10 meters per second is our change, 5 seconds, 2 meters per second squared. What's the acceleration at C?
0.
Yeah. All right, 0 meters per second squared. And how long did it take? Did it stay there? 5 seconds, right?
Yeah.
Okay. So now we're going to do D. And our change in D, first off, it's a negative change because it's going down, right? So it's a negative velocity change of 4 meters per second, and it happens over 10 seconds. So if we've got negative 4 meters per second squared, negative 4 meters per second divided by 10 seconds, we're going to get negative 0.4 meters per second squared. Okay, now our last one. Okay, all right, our last one. We have a negative change of, what is that, 6, and it is 6 meters per second over 5. So it becomes negative 6 meters per second divided by 5 seconds, and that gives us negative 1.2 meters per second squared. All right. So next thing we have to do, so now we have all of our accelerations that we're going to graph over here. Okay. Here's all of our accelerations. And we're going to graph them on this side. Okay? But what do we have to do before we graph those?
The biggest minus the least over
The scale. Yeah, the biggest minus the smallest. So that is max minus, this is the scale, max minus min divided by the number of squares. In this case, it's the exact same graph, so 16 squares. So it's 2 minus negative 1.2 divided by 16 squares. That gives us 3.2 divided by 16, which is 0.2. So basically our scale is 1 square is equal to 0.2 meters per second squared. Okay. So huh?
We start off on top?
Yeah, we're going to start off on top and see how this one is. It's even. All right, it breaks off even. We don't have to round anything up on this. That means that we have to do exactly this, max to min, to make it fit. Okay, we're going to start over here at 2. 2.0 meters per second squared. We're just going to go down 1.8, 1.6, and because of handwriting issues, I'm going to start skipping every other one. 1.6, 1.2, 0.8, 0.4, 0. Now we're going negative, negative 0.4, negative 0.8, negative 1.2. Okay. That's going to give us a y-axis that we can put in here. Whoops, not that. Okay, so here we go. There's our y-axis. We're going to put our x-axis in too. Remember, each time you change the filter, you go from one vision to another vision, it's still the same thing happening. So it's still the same horizontal axis. It's still the same time period. So as long as you have the same graph, same increments. So that means, I'm going to write this in red so we can see it. 5, 10, 15, 20, 25, 30, and label your axis. Time in seconds. Is this feeling familiar now? It's the exact same process that we did yesterday, right? Except now we just changed what are we looking at. I'm going to wait for pencils to stop for a second. Make sure everyone gets ready to go so we're all at the same place. It was going to go for a while. It was listening to me saying, I'm not going to stop. I'm going to escape. We're almost done, so I think you guys are going to be okay. For those of you who have to leave. So, for over segment A, we had for 5 seconds, it was a constant acceleration of 1. What does a constant line look like? Flat. Okay? So we are going to go, so conceptually what's happening is this. At 0 seconds, it was 1 meter per second squared. At 1 second, it was 1 meter per second squared. 2, it's at 1 meters per second squared. 3 seconds, it's 1 meter per second squared. 4 seconds, it's 1 meter per second squared. And 5 seconds, it's 1 meter per second squared. So if we're going to go ahead, we're going to turn that into something we can use. And then there's our best fit line. Okay? You don't have to put the dot in every time. Once you get the idea that this is flat because it's a constant, you're good to go. Okay, so for B, we've got, we got 2 meters per second squared is going to be our y value, and we're going to do it for a period of 5 seconds. So I'm going to go 1, 2, 3, 4, is that 5? There's my 5. All right, go ahead, I connect my lines. Remember, if they're straight vertical, just for visual ease, we're just putting that straight one there. Where's my next segment going?
0.
0. And how long is it going there for?
5 seconds.
All right, so so from 10 to 15, we're going to have this line. Okay, why don't you guys quickly or slowly do the next one?
Negative.
The next 2. And I'll come around and I'll talk to you if we need to.